In this video, we're going to finish off our topic of acids, bases and salts by looking at investigating salts. And just before we do that, let's go over the equations from page 12. So sodium hydroxide and hydrochloric acid, well, that's acid plus alkali given salt plus water. So sodium hydroxide and hydrochloric acid, and then that'll give us the salt sodium chloride. Hydrochloric acid gives chlorides, and then the sodium comes from that, and then water. Symbols equation, NaOH, sodium hydroxide, Na plus 1 OH minus 1, so sodium hydroxide. Hydrochloric acid, we have to remember HCl. Sodium chloride, NaCl, and water, H2O. And when you check either side of the equation, that's balanced, so don't need to add anything. Calcium hydroxide and sulfuric acid. So again, this is acid plus alkali given salt plus water. So the salt, calcium sulfate. So from the sulfuric acid, we get sulfate salts, and then the calcium from this, and then water being the other product. Our formula is calcium hydroxide. Common mistake here is just to put CaOH. Now, calcium's group 2, so plus 2. Hydroxide's OH minus 1, so Ca brackets OH2. So don't be surprised if you get it wrong, but do your best to get it correct if you can. Sulfuric acid, H2SO4. Calcium sulfate, Ca plus 2. Sulfate on the back of our data sheet, SO4 minus 2, so CaSO4, and then water. To balance it up, when you look here, there are 2 hydrogens here, and then 2 here, and 1 inside the brackets multiplied by 2, so 4 hydrogens in total. This side, we need to have 4 hydrogens over there, so a 2 in front of the water. And then that balances up the oxygens as well. 2 times 1 is 2, plus 4 is 6, 4, and then 2 times 1, 6 over on this side. Copper oxide, well, it's a base. So again, acid plus base given us salt plus water. So copper 2 oxide, hydrochloric acid, that gives us copper 2 chloride. Remember, we keep the 2 there. Copper 2 oxide gives us copper 2 chloride. And then symbols equation, CuO copper oxide, Cu plus 2, O minus 2. So CuO, hydrochloric acid, HCl. Copper 2 chloride, Cu plus 2, Cl minus 2. And then water, H2O, 2 chlorines and 2 hydrogens this side, so we need a 2 in front of the HCl. Magnesium oxide, also acid plus base, given salt plus water, so the salt magnesium sulfate, and then water. And then our symbols equation, magnesium oxide, MgO, Mg plus 2, O minus 2, sulfuric acid, H2SO4, magnesium sulfate, Mg plus 2, sulfate, SO4 minus 2, that's on the back of our data sheet, and then water, H2O. And when you check out the side, all the atoms are balanced, so we don't need to put anything in there. Calcium carbonate and hydrochloric acid, so this is going to be acid and carbonate, salt, water, and carbon dioxide. So, calcium carbonate and hydrochloric acid, calcium chloride, water, and carbon dioxide. Formulas, calcium carbonate, Ca, carbonate, if you look up the back of your data sheet, CO3 minus 2, so calcium's plus 2, so CaCO3. So just be careful of that one. Quite often people put CaC, and that's calcium carbide. Okay, then IDE, this is carbonate. So remember, if you see that ATE, look in the back of your data sheet, CaCO3. Other ones, hydrochloric acid, HCl, calcium chloride, again be careful of this, Ca is plus 2, group 2, chlorines minus 1, so CaCl2, water H2O, carbon dioxide CO2. And then when you look either side, 2 chlorines, 2 hydrogens, so we need a 2 in front of the HCl. Number 6, copper carbonate. So again, it's acid plus carbonate, salt, water, and carbon dioxide. So word equation, copper 2 carbonate gives us copper 2 sulfate. So sulfuric acid giving us sulfate salts, and then water and carbon dioxide. Formulas, CuCO3, so copper's plus 2 in the same way calcium was. Carbonate CO3, so CuCO3. Sulfuric acid H2SO4. Copper sulfate, Cu plus 2, sulfate SO4 minus 2, CuSO4, water, and carbon dioxide. And when you check out the side there, that's already balanced. And finally, magnesium and hydrochloric acid, well, that's going to be acid plus metal, salt plus hydrogen. So magnesium and nitric acid, magnesium nitrate plus hydrogen. Formulas, Mg, nitric acid HNO3. Now, magnesium nitrate, Mg's plus 2, nitrate NO3 minus 1. So we need 2 nitrates for every magnesium. So Mg brackets NO3, 2, and hydrogen H2. And don't forget about that. Don't forget to put the 2 there. Again, a common mistake is just to put the H rather than H2 there. When you put it that way, easiest way to say it is there's 2 nitrates, which there is here in NO3. There's 2 hydrogens, which is there. So we need a 2 in front of the HNO3. Okay, so to look at investigating salts, we look at a definition that SIA have told us that you should be able to give if it says, what is a salt? And a salt is produced when the hydrogen ions in acids are replaced by metals or by ammonium ions. Now, I want to try and show you what that means. So let's look at a couple of animations again. So hydrochloric acid being neutralized by sodium hydroxide. Now remember, acid plus alkali. And what we've got here is when they go into solution, you remember what all acids do is they give off H plus ions, and all alkalis give off OH minus ions. So what they'll ask you, what we've done so far, a lot of it is neutralization. And you remember that really what neutralization is the acid combining with the alkali, making water, which is pH 7. And in exams, they'll ask you for balanced ionic equations, or they'll ask you for the ionic equation during neutralization, and that's what they want there. Do you remember they want that H plus from acids combining with OH minus from alkalis, giving us water. The little bits underneath it, remember, are the state symbols. AQ for aqueous, dissolved in water, so acids are always dilute that we use, so they're dissolved in water. Similarly, alkalis are aqueous, and then water itself is liquid. So that equation comes up over and over again, and as we go through the past paper questions, you'll see that's asked quite a bit, so know that one. Now, what we're more interested in this video on is the salts, right? So what we've done is we've taken the H plus away from the acids. When the acid's been neutralized, that H plus has been taken away. Now it is replaced, and what it's replaced by is what was sitting beside the OH minus ions. Let's put those together. And you remember what we've made here is the salt, and in this case it's sodium chloride. So really what happened was the HCl had its H replaced by sodium, by the metal ion, and then that's what the salt is. So a salt is where the acid has its H plus replaced by a metal ion, sodium chloride. Let's look at another one. Here's hydrochloric acid with potassium hydroxide. So hopefully you'll see that's fairly similar, because when they go into water, the acid gives off its H plus. All acids give off H pluses. The alkali gives off its OH minus. They come together to give water. So you remember that balanced ionic equation for neutralization, H plus plus OH minus, AQ and AQ is shown dissolved in water, giving us water as a liquid, H2O as liquid. So that's the balanced ionic equation. Now, again, let's go to the salt. Well, this has had its H plus removed. It's replaced by the metal, in this case, potassium. And that gives us the salt potassium chloride. So again, the salt has been made when the H plus has been replaced by the metal ion. Let's take even a complicated acid like sulfuric acid. Now, sulfuric acid, H2SO4, it's got 2 H pluses attached to it. And then it can be neutralized by something like potassium hydroxide. Now, because it's got 2 H pluses, when we've done our balanced equations, remember we've had to put a 2 in front of things like that, so it needs 2 potassium hydroxides. So, put them into water. There's our 2 H pluses. There's our 2 OH minuses. And again, they come together to form water. And again, that balanced equation, the H pluses and OH minuses have given us water. And you could double everything up, but as long as you've got the ratio H plus and OH minus giving you H2O, that's the balanced ionic equation for the reaction. So again, it's still a neutralization. It's H plus from the acid combined with OH minus from the alkali, giving us water. Now, look at what's left behind this time. So this time, this, remember, is the sulfate ion. So the H pluses have been taken away, and here's the metals that can sit against them. So when they come together, they're going to give us potassium sulfate. This time the salt is going to be potassium sulfate. So again, the H pluses from the acids have been balanced or have been replaced by the metal ions. So salts are made whenever those H pluses are replaced by metal ions. Now, even, and this is, if you like, the worst case scenario with GCSE, Even things like nitric acid, which has got its H plus attached to it, so nitric acid HNO3, so there's its H plus, and it can be neutralized by ammonia. Now, in solution, ammonia exists as what's called ammonium hydroxide. So there's our ammonium hydroxide. And this is why ammonia is an alkali, because it's got an OH minus. So when we put it into water, the nitric acid gives off the H plus, the ammonium hydroxide gives off the OH minus. So the first part is exactly the same as before, water, H plus plus OH minus giving us H2O. And then the acid has its H plus replaced, and in this case, it's going to be replaced by that, the NH4 plus ion, the ammonium ion. And when we put those together, that makes the salt ammonium nitrate. So what we see then is that the salt is always made when the H plus from the acid has been replaced by a metal ion or ammonium. So if you look at page 13, then that's the theory behind it. There's only really a little bit of highlighting up. There's two little typos, by the way. If you look down there on the box, you can replace those two. And that whole table is really designed just as a quick look over. So if you look at it, it's really going on this definition. So highlight up that definition. There's what we talked about on the theory just earlier on. A salt is produced when the hydrogen ions in acids are replaced by metals or ammonium ions. So be able to quote that in an exam if they ask you what is a salt. And then there's the idea of it. So there's the acids, so the three acids, sulfuric acid, hydrochloric acid, nitric acid. You replace the hydrogen ions with either metals, for example, zinc. And if you're using zinc, you could use zinc or zinc oxide or zinc carbonate, or you could do of magnesium, again using either magnesium or magnesium oxide or magnesium carbonate, or ammonium ions using ammonium hydroxide. And then what you'll produce is the corresponding salt. So if you replace the H pluses on the sulfuric acid with zinc, it becomes zinc sulfate. If you replace the H pluses on the sulfuric acid with magnesium, it becomes magnesium sulfate. If you replace the H pluses on sulfuric acid with ammonium, it becomes ammonium sulfate. So that's really just a look over and see that definition. So acids have their H plus ions or hydrogen ions replaced with metals or ammonium ions, and then there's the salts produced. And then those other two boxes are just illustrations for hydrochloric acid. So again, using zinc, magnesium, or ammonium, and in this case you get the chloride salts. And then this is nitric acid. Again, if you use zinc or magnesium, you will get the salts there. Again, the zinc nitrate and magnesium nitrate. So that's the idea of salts. Now, okay, so to finish off, there's usually a little investigation that we do, which is looking at various salts and dissolving them. Now, to be absolutely honest about it, what you find is that there's actually only two sets of observations. One every time you get a copper salt, and one when you get all the other salts that we give you. So we set you out a range of salts like sodium chloride and potassium chloride and zinc and aluminium and so on, and we give you some copper salts. And we get you to look at them, record down the colour of the salt, and then the solution. And the reason for that is there's a trend. And what we really want at the end of this is the trend. So I will show you the two sets of observations in a short video in a moment, and then I'll give you the observations that you put in the table. And to be honest, you can put them in and get your table complete and so on. But the trend in the two boxes underneath are what you need to know. And that's really the only questions that come up on this. So let's show you the little video, which is really just showing you the two sets of observations. So the first one is dissolving the copper salts. So we put a little bit of water into a beaker. And then there's some copper sulfate, or copper nitrate has similar observations. Copper chloride, similar as well. And when you keep adding it to water, you can see that. So the copper salt is obviously a blue colour. And the solution, you see it gives a little bit of a greeny tinge, but whenever you get a dark enough concentration of it, you can see there it's obviously a blue solution. So copper salts tend to be blue in colour. And then when they dissolve, they give us blue solutions. And every copper salt does the same thing. Copper nitrate and copper chloride do very, very similar things. There's a little bit of green in some of them, but the solutions are always blue. And that's the key thing that they want. They want you to know that copper 2 solutions are blue. And what it means is every time you react a copper compound and you get a copper salt made, you get a blue solution. So do you remember from the videos we saw earlier on, we saw copper sulfate being that blue solution. Now, I'll run on and show you the other salts. So again, this is a video that was showing various salts being dissolved, and again, I'm not going to take time and show everything. You can see all the other salts are white powders, and when you put them into water and stir them, you can see the solutions look something like that. Colorless solution. So that clarifies a little bit more as the video goes on there, but not very much. And you can see colorless solution. So there's no color with this. So all of the other salts are basically white powders, and when they dissolve, they give us colorless solutions. So the pattern, so every time we've got a salt that's not a copper one, it's a white salt that gives us a colorless solution. Sodium iodide would be the same, white salt, colorless solution. And then we get a copper one. So copper sulfate, it's a blue salt. And then that dissolves to give us a blue solution. We give you a thing called copper ethanoate. So if you use ethanoic acid, you get ethanoate. We'll briefly talk about that next year with organic. Blue salt, that gives us a blue solution. So again, do you see it's the copper ones that are different from the others. Then we get magnesium, strontium, and so on. White solid, colorless solution. White solid, colorless solution. Aluminium, white solid, colorless solution. And then we get back to a copper one. Blue solid. We touch a green usually about copper nitrate, but mostly blue. And it gives us a blue solution. So the three copper ones that we've got there, 1, 2, 3, there's the key one there, the blue solution with it. And for all of the rest, white solid, colorless solution, white solid, colorless solution, white solid, colorless solution. So the key bit here is this. Here's the pattern. So the salts of metals of group 1, 2 and aluminium, so if you look at that, those are all potassium, sodium, strontium and magnesium, which are all group 2, and then aluminium. So any salts of group 1, 2 and aluminium are generally white, and they dissolve to give us colorless solutions. So they want you to remember that. So it means that, I think the easiest way to remember it is, if you think of sodium chloride, which is common table salt, you know it's white, so that helps you remember that. And then if you put that into water, it goes colorless. And then copper compounds are generally blue in solution. And again, you'll see that come up in past paper questions. Now, they have a variety of questions because they could ask you, what's the color of sodium chloride? It's white. What happens when dissolved in water? Colorless. Similarly, sodium iodide does the same thing. So if you remember generally group 1 and group 2 and aluminium salts, they're white, dissolve and give us colorless solutions. Copper give us the blue solution. And then last bit, just to finish off the notes, the two tests that we've used, and again, that's just to round off. So hydrogen, you remember, is the pop test. So usually there's 2 marks for this, or to get the mark for it, you have to have 2 points. And that is the idea of the pop, the little light explosion with a lighted splint. Now, not a glowing splint, it's not enough energy to cause it to pop. So it has to be a pop with a lighted splint. So put that in and put a wee star beside. That's the test for hydrogen. And for carbon dioxide, you've come across that a lot. But again, they expect you to know that lime water goes from colorless to cloudy white. So that finishes off our theory booklet. At the back of the booklet, there are some past paper questions. And if you go to the first page of these, there's one that we should have blanked out there, which is in the past they used to get you to do some of the salt preparations and then answer questions on. We'll do a wee bit more of that in year 12, but it's not in year 11 work. So you can blank out that B2 on that first question, but the rest should be okay. If you go through it, most of it should be based on what we have. You'll see on the screen there, if you see C, balanced ionic equation, think about what I talked about earlier on in the video. That's where H pluses from the acid are reacting with OH minus ions from the alkali, giving us water. So put that down with the state symbols, and look, you can see 3 marks for it. And you'll see you're asked to write balanced symbols equation, similar to what we were doing in the previous video, and so on. So have we go at the past paper questions, take a photograph of them, upload them to me, and then that finishes off our work on acids, bases, and salts.